Hi everyone, welcome to lecture number 5 of GATE DA course under probability and statistics. So in last lecture we saw independent events, and two events A and B are independent if probability of any one event doesn't affect, or basically happening of any one event doesn't affect the probability of other event, which means the probability of A given B has already happened is probability of A, and similarly probability of B given A has already happened is probability of B only. And if we rearrange terms, probability of A intersection B, which means probability of happening of both events, is just the product of individual probabilities, or PA into PB. And we saw a few axioms on it as well, like if A and B are independent, then A complement and B will be independent, and A and B complement will be independent, and similarly A complement and B complement will also be independent. They are very important, and we will see a few questions on that as well in this lecture. So this was the notion, if two events are independent if this condition holds. So now let's see an axiom. Okay, prove that an event A is independent of any event if probability of A is 1 and also probability of A is 0. So which means that when is probability of A 1? Probability of an event A is 1 if probability A is A is the sample space itself. It means it is just saying that sample space is independent of any event. So it is given that probability of A is 1, and it is saying that it will be independent of any event B. So let's say there is an event B. It can have a probability of PB. So it doesn't matter what event B is, event A will be independent with any event. Okay. So what does it mean? So in Venn diagram, this is A. Basically A is the entire universe. There is nothing which is not A. Actually I should draw it like this. If this is the universe is equal to A also, right? Because there is nothing which is outside A. Probability of A is 1 and B will be somewhere here, right? So what will be probability of A intersection B? See, what will be probability of A intersection B? Since probability of A is 1, A always happens. So probability of B is just probability of B only. A intersection B is what? It is B only. Since B is inside A intersection B is only B only, right? So probability of A intersection B is nothing but P, or probability of B. And we can always multiply 1. So it is also probability of B into probability of A. We are just multiplying it by 1. Probability of A is 1. So that's why if probability of A is 1, A will be independent with any event. Similarly, an event which can never happen. See, it is just like saying that an event which always happens will be independent of any event. It is like saying that, let's say you are throwing a die, right? And what is the probability of getting an odd number? It is 1 by 2. And now someone is saying that another event happened in which you got a number between 1 and 6. It is sure that you got a number between 1 and 6. We already knew we will get a number between 1 and 6. The probability won't change, right? So if someone is saying that universe happened, universe always happens, right? Like sample space will happen. So that's why it will be independent of any event. Similarly, second statement saying that nothing happened. It is like this is slightly like illogical. Like it is saying that an event which can never happen will be independent of any event, right? So what does it mean? In second case, probability of A is 0. So A can never happen. In this case, how the Venn diagram looks? This is universe, this is A. Basically, like A is nothing. A is nowhere. A is an empty set. And this is B. So since A is an empty set, A intersection B will also be an empty set. There is nothing in common. So probability of A intersection B will also be 0, which is probability of A times probability of B. Right? Since probability of A is 0, you can multiply 0 to anything, you will get 0 only. So that's why an event which can never happen is also independent of any other event. And this we have already seen that mutually exclusive events are always dependent. if they have non-zero probability. So if there are two events which are mutually exclusive, so which means they have non-zero probability also, like it is given that they have non-zero probability also, which means that probability of A is not 0, probability of B is not 0. And now it is given that since they are exclusive, probability of A intersection B will be 0. So it can never be equal to probability of A into probability of B since they are non-zero. So if two events are exclusive and they are they have non-zero probability, they can never be independent, they will always be dependent. This we have already seen in last lecture, right? So these were a few examples on independence of two events. Now let's see independence of three events. So this is slightly tricky. So we know that two events are independent if probability of A intersection B is probability of A into probability of B. Now three events A, B and C are independent if all of the following conditions hold. All the conditions should hold, which means A and B should be independent of each other, A and C should be independent of each other, B and C should be independent of each other, and A, B, C, which means probability of A intersection B intersection C should also be equal to PA into PB into PC. So this is like a definition, right? Like you will not see the proof, like that's not required. Like three events are independent if all the conditions hold. If any one of the condition doesn't satisfy, three events are not independent of each other. Okay, that's a very some people just only check this condition. That's a common mistake. Since in two events also you only check one condition, but that's not the case here. Okay, three events are independent if all the conditions are true. So you have to check the independence of AB, AC, BC and ABC. Okay, then only three events will be independent of each other. So for example, if we see this experiment, a ball is drawn from a bag containing four balls. A ball is drawn from a bag containing four balls numbered 1, 2, 3, 4 with each outcome equally likely. So there is a bag containing four balls 1, 2, 3 and 4. Now event E is getting 1 or 2. So you're just pulling out one ball at random. So what is the probability of E? Probability of E is 2 by 4, which is 1 by 2. Similarly, probability of F is getting 1 or 3, which means again like 2 by 4, which is 1 by 2. What is the probability of G? Again 1 by 2. Okay. Now what is the probability of E intersection F? What is common in both E and F? There is only one element common in E and F, which is 1. So it is like 1 by 4. Similarly, probability of E intersection G is also 1 by 4. There is only one element common. And probability of F intersection G is also 1 by 4. There is only one element common. And what is probability of E intersection F intersection G? We have to check four conditions here, right? What is probability of E intersection F intersection G? There is still one element common. There is still one element common, which is 1. So it is again 1 by 4. So is probability of E intersection F equal to probability of E into probability of F? Yes. They are 1 by 2 each. So E and F are independent of each other. Similarly, is probability of E intersection G equal to probability of E into probability of G? Yes. Since they are both 1 by 2, so E and G are also independent of each other. Is probability of F intersection G equal to probability of F into probability of G? Yes, because they are also 1 by 2. So F and G are also independent of each other. They are all pairwise independent. Now, is probability of E intersection F intersection G equal to probability of E into probability of F into probability of G? Is this correct? No. Because probability of E into probability of F into probability of G is what? 1 by 2 into 1 by 2 into 1 by 2, 1 by 8. It is not true. So that's why E, F and G here are not independent of each other. These three events are not independent of each other. Only they are pairwise independent. E and F are independent, E and G are independent, and F and G are independent. Okay, but they are not all independent of each other. All the conditions should hold. Okay. Cool. Now, given the independence of three events, we have some difficult theorems to prove. Okay, if A, B and C are independent, okay, this is very tricky now. All these conditions will hold. Like if A, B and C are independent, A union B and C are also independent. Similarly, A complement union B and C are also independent. A complement, you can take complement anywhere and take union of two sets. A complement union B complement and C are also independent. And all three, A complement, B complement, C complement are also independent of each other. So what does it mean? So whenever you have to prove something like this, like see, lots of variations can be asked. Whenever you have to prove, just draw the Venn diagram and try to find the intersection set and try to find the probability, okay? So it is given that A, B, C are independent. It means that the four conditions hold. A and B are independent, B and C are independent, A and C are independent, and P of A intersection B intersection C is equal to PA into PB into PC. All these four conditions hold. Now you want to find this. You have to prove that these are independent or not. So what does it mean? You just have to calculate the probability of A union B intersection C. That's what you want. This is one event now. A union B, let's say, is E. Then you have to prove that E and C are independent or not, which means that probability of E intersection C should be equal to PE into PC. That is your aim. That is what you want to prove. The probability of E intersection C should be equal to probability of E into probability of C. Now, how will I get this? So here you can apply the distributive law. So intersection gets distributed inside, right? So this will be nothing but probability of A intersection C union probability of, so it's like, this is nothing but probability of A intersection C union B intersection C, right? I just distributed intersection inside, like standard set theory laws. So you can also see it using Venn diagram. This is A, this is B, this is C. What do we want? A union B, it should be in A or B and it should be in C, which means that it should be in A and B and it should be in C. So A union B is what? This entire set. And also intersection with C is this set. So it is nothing but intersection of union of A intersection C and B intersection C. You see the union. This is exactly correct using Venn diagram. So what is it? Okay, we can just apply the De Morgan's law. We can just expand union, inclusion, exclusion. So it is like probability of A intersection C plus probability of B intersection C minus probability of A intersection B intersection C. Right? Just expanded the union. So what is probability? So we know that probability of A intersection C is probability of A into probability of C. Since A, B and C are independent, these are independent, these are independent, and this is independent. So this is nothing but probability of B into probability of C minus this is nothing but probability of A into probability of B into probability of C. Now you can just take probability of C out. This will become probability of A plus probability of B minus probability of A into probability of B. Right? See, we are getting where we want. This is probability of C times. We know that since A and B are also independent, we can write probability of A into probability of B as probability of A intersection B. So this is nothing but probability of A plus probability of B minus probability of A intersection B. Now this entire thing is nothing but A union B. Again, inclusion, exclusion. So it is nothing but times probability of A union B. That's what we wanted. So we have proved that this is equal to this, which means that these two are independent of each other. Right? So similarly, I can prove one more. So just do the expansion and like you will be good to go. Okay, like the same way you can prove the other theorems as well. We will not prove all of them. Let's try second also. what is probability of A intersection union B intersection C? Here also you can apply the distribution law. So it will become probability of A complement intersection C union B intersection C. Okay. So it is nothing but like you can just write it probability of A complement times probability of C plus probability of B times probability of C minus probability of A complement times probability of B times probability of C. And here also you can take probability of C as common, and you will get probability of A complement plus probability of B complement plus probability of B minus probability of A complement times probability of B. Now here this will be slightly tricky. Now since we know that A and B are independent, from the previous lecture we know that A complement and B are also independent, right? If A and B are independent, A complement and B are also independent. So we can write this as A complement intersection B, and again we will get the same theorem. Okay. So similarly you can prove the others as well. I will not do it. Consider these two as homework, and in the doubt solving session we will see like if you have doubts. So all of these will be independent if A, B and C are independent. Okay, it's easy to prove. Just apply a few set theory laws and you'll get the results. Cool. Now this is an example on the same independence of three events. So given that A, B, C are independent and their individual probabilities are given, you need to find this. So we know that if A, B, C are independent, A union B complement and C are also independent. In the last slide we saw that. We know that you can take union of two sets and add complement anywhere, it doesn't matter, right? So A union B complement and C are also independent, which means that that's what we want. We want to find the probability of A union B complement intersection C. That's what we want. This is nothing but probability of A union B complement times probability of C. Now you can expand this. This will become probability of A plus probability of B complement minus probability of A intersection B complement times probability of C. So it is nothing but probability of A plus probability of B complement minus. Now since A and B are independent, since A, B, C are independent, A and B are independent. Now if A and B are independent, A and B complement are also independent using last lecture. So this will be nothing but probability of A times probability of B complement times probability of C. Now we know each of these terms. We know PA, PB complement, PA, PB complement, PC. We know all of them. Everything is given. If PA is half and PB is 1 by 3, P of B complement is nothing but 2 by 3. 1 minus PB. So it's that. Okay, so you can very easily calculate this expression. And coming to the second example, what is probability of A complement intersection? We know that if A, B, C are independent, A complement, B complement and C complement are also independent. What does it mean? This is nothing but probability of A complement times probability of B complement times probability of C complement, which is half into 2 by 3 into 3 by 4, which is 1 by 4. Okay. So we are just applying the standard axioms of independence. Okay, similar to three events, we can have independence of n events. So now it will be like very tricky. So when independence of three events, you have to hold 4 conditions. If you have to have independence of, let's say 4 events, I will tell you. Let's say you want to, very easy, okay. A, B, C, D are independent if they are pairwise independent, they are triplet-wise independent, and all 4 are independent, which means that A intersection B should be equal to PA into PB. and similarly A intersection C, all pairwise, AB, AC, AD, BC, BD, 6 pairs, CD, okay? And then triplet wise also it should be true, which means that A, B, C should be independent, which means that PA intersection B intersection C should be equal to PA into PB into PC. Similarly, you should have A, B, D also true and B, C, D also true, okay? And there is one more, right? 4C3 is 4. ABC, ABD, ACD and BCD. Okay. So these 4 conditions should also be true. And also all 4 should be independent, which means that PA intersection B intersection C. So all possible cases which you can think of, which means taken 2 at a time, 3 at a time and 4 at a time. So if you have a sample size of n, like if you have n events, then NC2 plus NC3 plus NC4 and so on up to NCN. These many conditions have to hold true, right? Which is nothing but 2 to the power n minus n. Okay, you can prove that. So all these conditions have to be hold true. So if for n events A1, A2 up to AN are independent if they are pairwise independent, they are triplet wise independent, and so on, they are all independent. Okay. This is just need to know basis. GATE has not asked question on like independence of more than 3 events, but like you should know, okay, like all the conditions hold, then only they are all independent, otherwise not. Cool. So this is GATE 2000 question. E1 and E2 are events in probability space satisfying the following constraints. So it is given that probability of E1 is equal to probability of E2. And it is given that probability of E1 union E2 is given to be 1. And it is also given that E1 and E2 are independent, which means that probability of E1 intersection E2 is probability of E1 times probability of E2. These 3 things are given. Now what is the probability of E1? So let's say the probability of E1 is X. Let's say the probability of E1 is X. So what is this? So what is probability of E1 union E2? It is probability of E1 plus probability of E2 minus probability of E1 intersection E2. Right? Now probability of E1 is X. And probability of E2 is equal to probability of E1. It is also X. Minus probability of E1 intersection E2 is probability of E1 into probability of E2. They are both X. So X into X becomes X square. Now this is given to be 1. This union probability is given to be 1. So what does it mean? It becomes an equation. X square minus 2x plus 1 is equal to 0. Which means that x minus 1 whole square is equal to 0. It means that x is equal to 1. X has to be equal to 1. There is only one solution. So the probability of E1 is 1. Okay. Standard, like I just applied the equation, like we know that E1 union E2 is what, and then the independence, everything was given. Cool. Cool. This is another example asked in GATE 2003. Let PE denote the probability of event E. Given that PA is 1, PB is half, the values of PA by B and PB by A are. Okay, very easy question. I already told you that if probability of any event is 1, it will be independent of every event. Probability of an event A, if it is 1, it will be independent of every event. Axiom which we saw, okay, in the first slide. If probability of any event is 1, it is independent of any event, which means that A and B here are independent of each other. It means that it doesn't matter. Basically, A and B are independent, which means that probability of A given B has already happened will be equal to probability of A only, and also probability of B given A has already happened will be probability of B only. Even if you don't remember the axiom in the exam, we know that probability of A given B has already happened is probability of A intersection B upon probability of B. Now since probability of A is 1, probability of A intersection B will be probability of B only, and you can apply the formula. Okay, so the first thing is probability of A only. Probability of A is 1, so this thing is 1, And probability of B by A is probability of B, which is half. So 1 comma half. Okay. It is based on the axiom that we have seen. Cool. So this concludes independent events. Like we have seen, like this is the major portion in probability. Like most of the questions come from independent events, condition probability, and multiplication theorem. Now we will see some more complicated stuff like Bayes theorem in coming classes, and also there are a few notations in probability like total probability, joint probability, and marginal probability. We will see all this. Very important concepts and theorems coming up in the coming sections. Okay. So thank you. See you tomorrow. Bye.